Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to module 5.4. As you know, this week we have talked about a lot of concepts, and one of the important ones in this context is this idea of entropy. Because in a way, as I said, a lot of this course we have focused on this elastic resistor, and what makes elastic resistors easier to understand is that entropy-driven processes, which are of course an integral part of all of this, but they are all confined to the contacts. And in general, of course, they are all mixed up, and that is why we took a more general model here, where you could have energy exchange and entropy-driven processes even within the channel. Okay? But this important concept here is this concept of entropy, and this is where, I guess it was in the second module that I introduced this K log W, where W was the number of states available for this general system. You see? And what I'd like to do in this module actually is obtain a different expression for the entropy. I'll start from here, but I'll explain what that is. Something like this. Supposing we consider a system which has composed of lots of electrons, or actually lots of just non-interacting things, separate. And each one of these has a bunch of levels available to it, which could be occupied with different probabilities p sub I within that. But then there's lots of these identical systems, non-interacting. Okay? And when I talk about W, I mean the states of this whole big thing. And now, question is there a way I could write the entropy in terms of this one individual unit there? See? Because if we could do that, that would be a very useful relationship to have. Because lots of times, what we are considering is, again, like lots of electrons, and that one electron might have, say, 2 levels available to it. And you could easily write down the p's. And when you want the entropy of the whole thing, this whole complicated thing, if I could write it in terms of individual things, that would be very useful. And just to give you another example, supposing I have a collection of spins, things that can be either up or down. Now, question is, what is the entropy of a collection of spins, which it can be up or down, and it's random? So again, you want K log W for this entire collection of spins. But if you looked at one spin, it basically can be up or down. There's just 2 states. And you could write down what the write down the states available to one of them easily. But question is, how does that relate to this overall W? Okay? So that's what I'll try to do. And the final result would be something like this. See, I'll show that this is equal to minus K pi log pi sum over I. And I guess if there are a total of n such systems in the whole thing, then I'll put a minus n in front. So if an individual spin has 2 states available, then this I runs over 1 and 2. That's it, pi log pi. And then n is just the total number of spins. So what I'm trying to do then is go from here to here. So this W is a function of these individual probabilities. Question is, how do you do that? Okay. So let me try to do that. So the way you do it is something like this, that when you have these n systems, n of them, then how many of them would be in some state, say n1, which would be like, P1 is the probability, Pi is the probability that an individual one is in a state I. So Ni, that is the number of these systems that are actually in the ith state, would be n times pi. Okay. Now, overall then, if you wanted to write W, how many states are available, that is where you can use this standard combinatorial principle, which says that, well, if you have n objects and n1 of them are like the same, they're the ones in which the system is in state 1, n2 of them are the same, and 3 of them are the same, these are all the various i's, then the number of ways you can arrange them is this factorial n divided by factorial n1, factorial n2, factorial n3, etc. So this would be what is W. And question is, how do I find the entropy? That's this log W. Well, I could take the logarithm there. And that would be equal to then logarithm of factorial n minus logarithm of factorial n1 minus logarithm of factorial n2, etc. And this is where, because these n's are large numbers, people use this Stirling's approximation. So this is log W. And the Stirling's approximation goes like this, that logarithm of factorial n is written as n log n minus n. And this is approximate, but it's a very good approximation for large values of n. So if you use that, you get from here, actually, let me write it up here. I'm starting from this expression. So let's write log of W is equal to, so logarithm of factorial n, that's like n log n minus n, and then logarithm of factorial n1, so that's like n1 log n1, but then minus n1, and then minus n2 log n2 minus n2, etc. And the second line just sort of cancels out, because n is equal to n1 plus n2 plus n3. When you add them all up, this and this will all just cancel. So what I really need is just the top part. And this part you could write as n log n, and then n1 is np1. So this is the probability of this one individual system being in state 1, that's np1, and then it's logarithm of np1, and then np2, logarithm of np2, etc. Now, this I could separate out into two parts. So there would be a logarithm of n, and then there would be a part that would be logarithm of p1. Similarly, this will have a part that's logarithm of n, and then a part that's logarithm of p2. Now, what you can see is that that first term, when you add them all up, will cancel out, because you see you have np1 logarithm of n, then you have np2 logarithm of n, and you're adding them all up, and the p's all add up to 1, because the probability is, of course, for this individual system, it has to be in one of its states. So p1 plus p2 plus p3, all that adds up to 1. So this all just cancels. This all just adds up to give you n log n, which cancels this one, you see. And so what you're then left with is p1 log p1. So minus p1 log p1 minus p2 log p2 minus p3 log P3, etc. You see? And this is the basic result that, oh, I guess there was the n, of course, in front of all this, P1 log P1, but this whole thing is, of course, multiplied by n. And if you'll notice, that's exactly what you have done here. You see, what I just did was we tried to write log of W, and I got n times this. And then, of course, S is k log W, so you put the k there. And so that gives you this expression for the entropy. And again, the picture to remember is that we are thinking of a collection of identical objects, lots of them, and each one has a bunch of states that it can occupy with various probabilities. See? And this form, you see, you can relatively easily apply to different systems. So for example, as I said, supposing we had these individual systems where spins that could be up or down, let's say. Now, so you could say, well, it has a probability of being up, let's say is half, and the probability of being down is, say, half. So when I have this random collection of spins, then what would be the entropy? Well, the entropy will be minus nk, and the summation over I then has to sum over those two states, and each one has a pi of half. So I'll have half log half plus half log half. And log of a half is, of course, negative logarithm of 2. And so there are two of them, the half cancels. So finally what you get is nk log 2. So the entropy then of a collection of spins, each one of which can be in this up or down state, overall entropy would be nk log 2 if it is random. On the other hand, if you had a system of spins where you knew that each one is in a particular state, up, let's say, you know that exactly everyone is up. Or let's say, for various reasons, the down is not even allowed. It's always up. OK, then you have just got one state. And then p log pi is just 0. Then there is no entropy associated with that. Okay. Now, if you know if those are all fixed. Now, one of the other things that comes out of looking at it this way is that there is a similar expression for what is called entropy in information theory. And that looks something like this. That doesn't have the S in it. That doesn't have the K in it. So this K you see is Boltzmann's constant, which is joules per Kelvin. It has dimensions. You know, kT is energy. So K is joules per Kelvin. It's got dimensions. But the way you define information entropy, I think they usually write it as H, probably. It is this Shannon's entropy. That would be minus, sum over I pi log pi. So if you, and here you are thinking of n bits of information, and then you put the n there. If you had n bits of information per bit, the amount of information would be that much. And if each bit a priori had a probability of being in one of two states, so the bit could be 0 or 1 with probabilities, say, p and 1 minus p. Then this, when you do the summation, you'd end up with minus p log p plus 1 minus p log 1 minus p. Okay. And the information content then, the way it is defined is, the way you think about it is, so you have this bit stream, and if you didn't know what state it is in, then there is, you could think of it as if then the entropy, in other words, it could be in all kinds of possible states, and the entropy is a measure of that. And as soon as you know that it is in a particular one, you have got the information transmitted. You have some information there. It could have been 100 different things, but you know one of them. So in that sense, this would be then a measure of how much information it carried. So this is what's usually called the Shannon's entropy. But the thing is, it is dimensionless. And one of the questions that often comes up, that people talk about a lot, is whether this has any connection, or what the connection is to the thermodynamic entropy. Where, because this is something this is something has dimensions, you can measure it, and so on. Okay? And one of the things I'd like to, I guess we'll finish up in the next module with this idea, is that if you have so let us say we have a collection of spins. So let us say we have this collection of spins, which you know is exactly all up, which means you know that its entropy is 0, because you know that this all happens to be up. Of course, if you let it equilibrate, with its surroundings and interact, then it will eventually all become random. Some up, some down, etc. It will all become random. And so the entropy eventually will be nk log 2. Okay? So this is a case where if you looked at the free energy change, this is this concept that I had mentioned earlier in the context of entropy, that if you looked at the free energy, okay, because the total energy, you could say, is the same here and here, because these are non-interacting spins. Doesn't matter if they're all in the same direction or if they're random. The energy hasn't changed, but the free energy is changing. So here, the free energy was, again, E minus Ts. So that's 0 in this case. Whereas here, if you looked at the free energy, it would be E minus Ts, it would be like minus nkt log 2. And this, of course, is the equilibrium state. The equilibrium state always has the lowest free energy. This is the equilibrium state. This was a special non-equilibrium situation, right, where we knew exactly what it was, and that's what gave it this 0 entropy, and the free energy was higher. And what we can show, and that's what I'll get into, as we sum up in the next module, we'll talk about this, is that we could easily conceptually construct a device in which, you see, this surrounding, let us say, is in a state where they are all up. So let us say we have a collection of spins that happen to be all up. That's the collection whose free energy is 0. And eventually, as you wait, it will go to a free energy of minus nkt log 2. The free energy will decrease. And what we can show is that in the process, as it does that, if we constructed this device cleverly, then this change in free energy we could extract in the form of useful work. So in other words, we could use this to make a battery, essentially, where you'd actually be doing something useful, like lighting up a light bulb schematically. So And the interesting point here is that you see, if going from here to this random situation, the energy hasn't changed. So you might say, well, I am lighting up a light bulb. I'm doing something useful. Where did all that energy come from? That energy didn't come from this collection of spins at all. But where it came from? Well, it just came from the surroundings. So in effect, you'd be actually doing what second law ordinarily says you cannot do, namely take energy from your surroundings and use it as useful work. Except that in this case you can, because you started from something that was in a highly non-equilibrium state, you see, with a higher free energy than it should have. And so one way you could say it is, well, originally you had this information. You knew about what state the system is in, and so you had complete information about it, and so the entropy was 0. And in this case, since no energy is involved, that also means the free energy was 0. And then you're using that information to actually extract useful work from it. So it kind of shows how you can convert information to work. And what I'd like to argue, and that's what we'll talk about in the next module, is that if you use this Shannon's entropy, which is a measure of the information, and when you multiply it by k, you get the regular entropy. And the point is that if you have this information in the form of, let's say, all spins in the same direction, for example, you know exactly where it is, you could extract energy from it. You could use this to extract energy. And in the process, of course, the information will be lost. You knew they were all up. By the time you're done, they'll be all random. The information is lost. But you have used this to do useful work, to get energy out of it. And how much energy can you extract from it? Well, exactly the change in the free energy that results. The free energy originally was 0 because the entropy was 0. And in this example, what is nice is that no real energy is involved. What I mean by that is, if this state had a higher energy than this, then that wouldn't be too surprising that as it relaxes, you can extract energy from it. I mean, here is something that was in a metastable state with some extra energy. And then as it relaxes, you built a clever device to use that, to extract that energy. That doesn't seem too unusual. What is special about this one is energy hasn't changed, because a bunch of spins all pointing in the same direction and a bunch of spins pointing randomly all have the same energy, as long as there's no interactions among the spins. So it's all the same. Energy hasn't changed, but the entropy has. And that change in entropy, that change in free energy, kind of allows you to extract that much amount of energy from your surroundings, from the heat all around you. Of course, how much you extract depends on the temperature. At 0 temperature, you couldn't extract anything. But at any other temperature, you'd be able to extract that much and turn it into useful work. So in a way, you are converting information into work. So basic point is that if you start from a system which is in some non-equilibrium state, whose free energy happens to be greater than what it should be at equilibrium, then as it relaxes to its equilibrium state, that difference in free energy is something you can extract in the form of useful work in principle. You could always construct an intelligent device to do that, which will convert this free energy into work. And the free energy has two parts. It has this E minus Ts. And the fact that the energy change you can extract, that doesn't seem too surprising. The interesting part is this one, which kind of corresponds to the informational aspect of it. That if there was more information here than here, then that allows you to take energy from elsewhere and turn it into useful work. And this is the thing that we'll try to finish up in the next module.